Okay, section 6.6 was not labeled in your notes packet, but it is the solving equations with exponentials and logarithms. So I've separated them out into about 5 types. Now, some of the equations you'll see and be able to recognize right away. Others are going to need a little bit of manipulation before they'll fit those patterns. But we're going to work through some examples and hopefully be able to start being able to spot how to tell which type it is. So the first type is a one-to-one property. I'm going to be doing a whole lot of highlighting. So if you don't want to highlight everything, that's fine. Of course, it's always your notes. The strategy when we have a one-to-one property is that we first have to combine so that we have a single same base on both sides or a single same log on both sides. And then we're able to use the one-to-one property, which says if a to the m equals a to the n, then m equals n. So what that looks like when you're working a problem is like if I had 4 to the x equals 4 to the fifth, then we could say x equals 5. Works the same way with logs. If log base a of m equals log base a of n, then m equals n. So say I had log base 4 of x equals log base 4 of 5, then we could say x equals 5. Now, when you have a logarithm, you have to make sure that you check domain. The argument has to be greater than 0. So anytime you have an equation that has a logarithm in it, you want to pay attention to that. So in this one that we just looked at, the domain would be right here, log base 4 of x. So we'd have to make sure that x has to be greater than 0, which it is because we got x equals 5. So we're good on that. Another type is when you have all logs that have the same base. So it's important that they have the same base. If we have all logs that have the same base, then what we're going to do is combine our logarithms so that we end up with one logarithm on each side of the equation. And then we're going to go back and use the one-to-one property that we just looked at up here. Sometimes we have to continue on and solve beyond just the one-to-one property. And then since it had a logarithm in the equation, we'll have to check our domain. So this would be like if we have log base 2 of x plus log base 2 of 3 equals log base 2 of 15. Then we would combine these to make it log base 2 of 3x equals log base 2 of 15, which would give us 3x equals 15 or x equals 5. And again, watch the domain, which would be this one right here. Since these two logarithms don't have variables, they won't have any domain restrictions, only the ones with variables. So the domain would also here be that x has to be greater than 0. And we got x equals 5, so domain is good. Another type would be if we have some logs and some numbers. And the strategy there is to move all your logarithms to one side and numbers to the other. Combine your logarithms into a single logarithm. Then go ahead and convert it from a log to an exponent. Solve. And make sure, since we had logarithms in this, that we check the domain. So I'll give you a simple one. Let's go. I'll piggyback on that one. So let's say we had log base 2 of x plus log base 2 of 3 equals 2. Then we would want to combine these two together. So we get log base 2 of 3x equals 2. And then convert from logarithmic to exponential form. So the base stays the base. So 2 up to the second power would equal 3x. So then we would get 4 equals 3x. So x would be 4/3. And we'd have to check our domain. Going back to the original, this one doesn't have a variable, so it's only this one. The domain would be that x is greater than 0. And we got 4/3, so that checks out. Variables in the exponents. Now this is a different scenario than this one where we had the one-to-one property. Sometimes this type becomes a one-to-one property, sometimes it does not, but it can be its own specific type. So what we'll do in that case is we'll isolate the base that's up to a power, take the log of both sides or natural log of both sides, and bring the power out front, and then solve. Okay. So say we had 5 plus 2 to the x equals 3. That's not going to work. I could have just made it an 8. That's fine. Let's make it an 8. So then we would want to isolate base to the power. So subtract 5. So then we get 2x equals 3. And then we'll take the natural log of both sides. So natural log of 2 to the x equals natural log of 3. Then we can bring that exponent out front. So we have x times natural log of 2 equals natural log of 3. And then we would just divide both sides by natural log of 2. So x would equal natural log of 3 divided by natural log of 2. And then the last one is factoring by U substitution. Now we've seen this in previous chapters, and it's going to work very similarly. So if you have like something e to the 2x and something e to the x, the e to the 2x is your u squared. So 5e to the 2x plus 2e to the x becomes 5u squared plus 2u. If you have 5e to the 4x and 2e to the 2x, your u squared will be the higher power, the one that's the double of the power. So we make those substitutions, then we solve for u, and you're going to get, one number for u or two numbers for u. But then we replace the u's with the original equation. So e to the x for the first one and e to the x, 2x for the second equation, and solve for x. Okay, so what do I mean by that? That sounded a little confusing. So on this one, where we had 5e to the 2x plus 2e to the x minus 7, then if we factor that, let's see, that would be 7 and 1. This guy's plus, this guy's minus. Okay, so we would get u equals negative 7/5 or u equals 1. Then we replace the u's from the original equation. So in the first equation, it would be e to the x because I replaced the u for the e to the x. So in my first equation, I would then do e to the x equals negative 7/5 and e to the x equals 1. In my second equation, I would have done e to the 2x equals negative 7/5, e to the 2x equals 1. So when that says solve for x, then essentially what we're going to do at that point is convert to log form. So since these are e to those, then it becomes natural log. So I would have natural log of negative 7/5 equals x on this one. I would have natural log of 1 equals x on the other one. So looking at this, I cannot have negative 7/5 in the argument to my log. So this one would not be a solution because negative 7/5 is not in the domain of natural log. And then natural log of 1 is 0, so that gives me x equals 0. And in the other form, when I convert, I would have natural log of negative 7/5 equals 2x. which still is not going to be a solution, or natural log of 1 equals 2x. So that's still going to give me x equals 0. Okay, we're going to see several examples and talk about how to recognize which type they are. But that's the general rundown of what you can expect to see after we do manipulations. So, solving equations. What type is this one? This one is all logs, and they have the same base. So this is that all logs with the same base. So we have to combine our logarithms, so there's only one log on each side, and then we'll use the one-to-one property. But at this moment, this 2 that's out in front here is problematic because it's not just a log on its own. So we are going to need to move this 2 up. So then we will have log base 5 of x plus 12 equals log base 5 of x squared. Then we're going to use the one-to-one property. The one-to-one property is going to allow us to write a new equation that says x plus 12 equals x squared. And then we will solve that. This is a quadratic equation, so we will be solving by factoring. So I'm going to move all my terms onto the same side. Then I'm going to factor. This becomes x minus 4 times x plus 3. And use the zero product property to figure out that x can either equal 4 or x can equal negative 3. Now, this is one of the equations that we have to be looking at domain because we had logs in our original equation. So I'm going to need to be looking at the domain for my original equation by setting the arguments of the log greater than 0. So over here, I'll consider domain. I have to look at x plus 12 is greater than 0 and x is greater than 0. So x has to be greater than negative 12 and x has to be greater than 0. Since I have two separate ones, I have to look at the most restrictive domain. So that's going to be this one. So all of my x values would have to be greater than 0. So if I look at the solutions that I got, I can exclude, or I have to exclude x equals negative 3 because it's not in my domain, but x equals 4 is. So this equation would have one solution, and that would be x equals 4. Okay, this guy, 10 to the 2x minus 3 equals 1/10. Now we can manipulate this a little bit, and we'll notice that we can turn it into a one-to-one property. So I already have 10 to the 2x minus 3. If I had 10 to some power on the other side, it would be a one-to-one property. I remember that this 1 over 10 I could rewrite as 10 to the negative 1. And that's going to lead us straight into that one-to-one property. Because I have two bases, two of the same base equal to each other, I can set their exponents equal. So that gives me 2x minus 3 equals negative 1. Add that 3 over, so 2x equals 2. And that is x equals 1. So let's talk domain. We've already said that if there is a log with a variable in it, today we've said that we have to look at domain. So what are our 3 types of domain concerns? From a long time ago, if we had variables inside an even index radical, we have to look at domain. If we have variables in the denominator, and now if we have a log, any base whatsoever, with variables inside the argument. So looking at this problem, we have none of those domain concerns. So the domain for this problem will be all real numbers. So when we get finished solving, we don't have to worry about any of our solutions being extraneous. All right, next problem. Log base 3 of 2 minus x equals 4. This one is some logs, some numbers. Some logs, some numbers. So our strategy on some logs and some numbers was to move all the logs to one side, numbers to the other, combine to a single logarithm, and then convert. So we already have it combined to one log, and all the numbers are on the other side. So we are ready to convert. So when we convert this from its logarithmic form to its exponential form, the 3 is going to get out of the log relationship and get into an exponential relationship with the 4. So the 3 becomes the base because it already was the base, goes to the power of 4, and then equals the original argument of 2 minus x. Now we can do 3 to the 4th power. 3 times 3 is 9, times 3 is 27, times 3 is 81. So 81 equals 2 minus x. Subtract that 2 over, 79 equals negative x. So x equals negative 79. Now, being that this had a log in the original problem, we need to be thinking about domain. The argument of that log needs to be greater than 0. So if I subtract that 2 over, I get negative x is greater than negative 2. Divide both sides by negative 1, I get x is less than 2. So we have to remember to reverse that inequality when we divide both sides by a negative number. So our domain is x is less than 2, and negative 79 fits that. So this is a valid solution. So sometimes people get confused because they think they can't have a negative answer when they have a log in the problem, but that's not necessarily the case because we had a negative solution. You just have to make sure that the argument is not ever negative. If I put negative 79 in for x, I would have 2 minus negative 79, which makes 2 plus 79. So I'd be taking the log of 81. And that's perfectly fine. Okay, whoop, my paper is sliding. Going to keep sliding. This type of problem here. This looks like variables in the exponents, but it's not by itself. Remember, I have to isolate the base to the power. So before I can do the converting step, I'm going to need to divide both sides by 2. So then I would have 1.00625 up to the power of 12t equals 4. And now this is variables in the exponents. So first thing we needed to do was isolate the base, so that now we have a variables in the exponents. So what we want to do is take the natural log of both sides. That's our strategy. I prefer natural log. That's just like my go-to instead of log, but you can definitely use common log. So I will then have the natural log of 1.00625 to the 12t power equals the natural log of 4. Now the whole reason we take the natural log of both sides is because I need to get this variable out of the exponent. And once it's in a log, I can bring that to the front of the equation, or the front of the logarithm. So now I have 12t times natural log of 1.00625 equals the natural log of 4. And then I'm going to divide, like what I need to do is get my t by itself. So to isolate that t, what I want to do is divide both sides by the 12 because it's multiplied by 12. And I also want to divide both sides by the natural log. I can do that in one step because remember that since multiplication is commutative, I could put the t to the front and leave it 12 natural log times 12 natural log of 1.0065. So we are allowed to legally do this. And then that leaves us the t on the left side, and it equals the natural log of 4 over 12 times the natural log of 1.00625. Now let's consider domain. Our original problem had no logarithms, had no variables in the denominator, had no variables inside even indexed radicals, so there are no concerns of our 3 things to watch out for. So the domain is unrestricted at negative infinity to infinity. So this actually is our solution. Now, at times, you may be asked to find a decimal, like a decimal approximation, and then you'll go to your calculator. But I prefer just to see the answer looking like that. If you used a different base for your log, like if you used a common log, then you would have log instead of ln. But that's fine too. Either is acceptable. Right. For that matter, any base would be acceptable. We do have several more examples, but I think I'm going to end this video and start a new one so that they're not super long.